Yeah, welcome everybody to the whatever lecture number 22 or so in our 2-semester intro crypto sequence. What we did over the last 4 weeks, I believe we spent about 2 weeks talking about digital signatures, and we found out that we could do some cool things with digital signatures. And then we learned about hash functions, which I introduced as an auxiliary function, as a Hilfsfunktion. For digital signatures. So we said, we needed hash function to digital signatures to sign long messages. What we're going to do today is we're kind of combining two topics. The main theme will be MACs, which stands for message authentication codes, which you can roughly think of as being digital signatures, but realized with symmetric cryptography. Okay, and they're pretty cool and fast, blah, blah, blah. And then when we actually want to build a MAC, how to build a MAC, we use the HMAC, which stands for hash-based MAC. So we will use hash function to realize actually a MAC. So it's kind of a cool, interesting lecture. It's very practical what we're going to do today. So first chapter of today is Introduction to what are MACs, to message authentication codes. Maybe first a remark about the terminology. MACs are also called and I do really like that name, cryptographic checksums. I think it's more descriptive. I like it better. Okay, so what is this all about? What we do want to do, we want to authenticate a message. And what we maybe let's write that down, recall what we did with digital signatures. The motivation for digital signatures the main motivation was, we tried to solve this problem in the digital world. In the real world, you have your, Bachelor of Science, diploma, Urkunde, and then it, in order to prevent that you do that with Photoshop at home, it's being signed by the department head or somebody. So we tried to move this act of digitally signing, that means assuring that it's coming from the right person, this sender authenticity, we tried to realize that in the digital world, and that was the original motivation for digital signatures. So, and we called that authentication, or sometimes also called sender authentication. Sorry, message authentication. So how did we do that? And that's how we, started, I think 3 weeks ago. Or 4 weeks ago, we talked about digital signatures. And now it's a little bit, Groundhog Day, that movie? Groundhog Day? Und täglich grüßt das Murmeltier, right? Who knows that movie? So you're going through that. So I'm doing exactly, if you look on the video what we did 4 weeks ago, This is how I started. I said we have this message, X, and we try to compute a digital signature here. And we had some signature algorithm here with K private. And then we turned that into a basic protocol. Where Bob has a public key pair and he publishes his public key. And if Bob now wants to do something like a signature and Unterschrift, he runs his whatever RSA or Elgamal signature algorithm or ECDSA, whatever is out there, and he computes the signature of X using his, of course, using his private key. So only Bob can do that. He transmits message and together with signature. And what does Alice do? How did we call this operation here? Verification, very good. So Alice runs the verification algorithm, which has X and S as input, but she's using the public key, and the statement is either true or false. Okay? So that was murmelt here. Okay? Very, very short. That was Groundhog Day. So what we're now trying to do is to do the same with symmetric cryptography. Let's try the same with symmetric algorithm. What is a possible motivation? Why would we do that? I mean, we're pretty happy, that works, very secure, blah, blah, blah. We get non-repudiation, all these funny things. What is a possible motivation? What is the motivation for moving away from public key-based signing and verification? Very simple answer. Yeah, it's faster, yeah. They're really great. You can do wonderful things. You can do key exchange over unsecured channel. You can do all these marvelous things with public key cryptography. They are really slow. They are a pain to do. So if you don't have to do it, it's really nice to have an alternative. And there are many situations where you can use HMAC, where you can use symmetric block ciphers and hash functions, and you get very similar results. Not identical results, so there's still a need for using digital signatures, but in general, it's not bad to have that available, symmetric cryptography. So how would that look? Again, we argue on a very high level without looking in the algorithms. If we want to do that symmetrically, we have Alice and Bob again. So now Bob does not have a public-private key pair, obviously. He only has his symmetric key, which he needs to share with Alice. So how does he share? Well, he has to build a secure channel, right? We know that. To get the key over. Which is not easy, but this is part of public key cryptography. And this is actually something we're going to solve in the next 2 lectures. We're going to talk about key distribution, or next 3 lectures maybe. So now what we did here, we computed the signature. We do something quite similar here. We compute but instead of a SIG SIG algorithm, we call that MAC for message authentication code. Input is, surprise, surprise, is again the message X here. we use a symmetric key at this point, and what comes out we call M, which is just terminology. So instead of S, we call it M. Yeah. Which is not nice because many books use M for message. You know, we call the message X, many books call the message M. Then Bob transmits, as before, X. But instead, now again, you have to append the signature, which is this MAC result. Or cryptographic checksum. Cryptographic checksum is being appended. So what we did here is, for digital signature, we had to run the verification algorithms. If you go back, you look at El Gamal digital signatures, you found that signing and verification are quite different operations, actually. You know, they both somehow play around with the discrete logarithm problem, but it wasn't particularly similar otherwise. Here, this is symmetric cryptography. So what we do here, we do exactly the same that we did at this point here. Okay, it's exactly symmetric setup. That means Alice, her verification step is mainly recomputing the MAC, so she also computes X. She gets M out, which we call M prime, M strich. This is not the verification per se. This is just doing a stupid computation here. What is now the final verification step? What does Alice have to do so she knows that this is really the original message here? What is the next line here? What does she have to do with this M prime? Very simple thing. She has to verify by comparing. So is this M that Alice computes, is that identical to this M? And you know, I use this kind of goofy notation here, Gleichheitszeichen mit Fragezeichen. Okay, this is only the notation, this is the only place in the world that's using that. I'm exaggerating, but this is not a standard notation here. Definitely not in cryptography. I think it's useful. Okay, so this is the basic setup. This is high-level description how MACs work. You have a symmetric key, Bob computes the MAC, Alice recomputes the MAC, the receiver recomputes the MAC, and then the receiver compares the two results. That's the idea. And what we can do, and then we did this with digital signatures, and it's getting easier and easier because we did that already, we can just look at this protocol and now start discussing properties. Again, without jumping into these algorithms. This will be second chapter of today, how to realize the algorithms. But right now we just stick with this very high level, very simple protocol and discuss properties. Properties of MACs. What would be nice to have, which actually we did not have with digital signatures, is to remember one problem with digital signatures we had is with RSA. It's maybe easier. If you want to sign RSA and you use RSA with a 2000-bit modulus, the message was restricted to 2000 bits. So you could only sign messages, with a length of 250 bytes or so, which is a pain in the neck. And then we had to introduce hash functions and hash them, blah, 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 blah. What would be nice to have is that right away a MAC could accept arbitrary length messages, and this is given. In the MAC case, we can use arbitrary input length. That means you can run a MAC immediately on an email of length 100 characters, or you can run that on a PDF file with 100 megabytes. You don't have to do hashing in between. What would be very nice, talking about this very practical input-output behavior, You know, if you put in 100 characters here, we probably get a short MAC out. What would be nice to have if you put in a PDF file of 100 megabyte, it would be nice if this still stays short, you know, that you have a short cryptographic checksum for any messages independent of the input links. And again, this is given. We have a fixed output length. Maybe singular is better here. Now, in terms of security services, the main thing we try to achieve, if you, shifting one more time, we wanted to have this message authentication. Message authentication means if you give a message, you know, that claims to be coming from Bob, it is actually coming from Bob and not from, in particular, not coming from Oscar. And this is, oh yeah, let's discuss it. So what happens if this checks out here? You know, if this is M prime is exactly, you know, the same 128 bits as M, does Alice know that this message is coming from Bob? Yes or no? What do you think?
No.
Why not? Who else could have, yeah?
Oscar could use a different key and match the X with this key. And
Yeah.
then he sends both the X and the UN.
Yeah, but Alice doesn't have Oscar's key. Good discussion. Good idea. It doesn't work, but it's a great discussion. So Oscar cannot do that because what does somebody has to know if you want to compute a valid M? You have to know the secret key. This is a very good wrong input. The answer is yes. We do have message authentication. If this checks out for Alice, she knows, well, this must have been computed by somebody who knows the K, and if this is always the assumption. This has been the assumption for 2 semesters, even though you might not notice it. All these protocols only work if the key distribution works. You know, of course, if Oscar has K, the whole things fail, but that's why we call that a secure channel. Otherwise, we would call that a leaky channel or something. So, no, we do have sender authentication, message authentication. Message authentication. Colon, Doppelpunkt. Alice is certain that Bob sent the message. This is great. So we have this, in which we call the security service. So we have a very important security service. It's really coming from Bob. The next thing, let's assume that's a financial transaction, and the semantics, the meaning of X is transfer $10 to Oscar's account. And now, you know, little mean Oscar, the bad guy, he would like to replace that by X tilde and turn the $10 transaction into a $10,000 transaction or euro transaction. So, what's going to happen here? Does Alice notice that? Can Oscar do that, and does the verification check out? This is my question, yes or no? No, of course not. You have a different input. We don't know the details. You know, it's probably something with block cipher, the hash functions. And if you flip one bit, the whole output will be random. So this doesn't work. You know, you can do that, but then you get this fat, you know, it's really bold. No, this is not equal. So verification fails. Meaning, in terms of security services, integrity is given integrity colon manipulations in transit, bei der Übertragung in transit will be detected by Alice. And then there was a third very, very, very important security service related to digital signatures. Anyone know what's the big thing? And I had this example with buying a Golf Volkswagen online. And how was the security service called? You know, Bob orders a car online, and then later on he doesn't want to have the car. And how was that security service called? Does anyone recall? German or English is fine. Nobody knows? Yep. Non-repudiation, nicht Zurückweisbarkeit. Non-repudiation. I guess we're pretty low tech here. What does it mean? This is a scenario, and we did talk about that a few weeks ago. X is the car order, right? Bob is ordering a car, Alice is a car dealer, and he sends over the order, whatever, like a web form that he fills, a contract together with his signature, his HMAC. Alice checks it out, blah, blah, blah. So later on, Alice claims, I never generated X. And Alice is dragging Bob to the court, for Gericht zerren. What's going to happen here? Can Bob prove towards a judge, towards a Richter, that Bob generated the message? Any ideas? It's really, Bob is saying, I never created that. Okay. And is it possible to prove? Yeah.
Yeah, because Alice could have sent it, could send the message to herself. And then say,
Exactly. Alice could have generated. This is the thing. It is a symmetric setup, so of course Bob can generate it, but Alice can generate it. So if Bob claims to a third party, I never generated that, Alice did it, a third party, a judge, a Richter, cannot decide who did it. So we do not have non-repudiation. Non-repudiation is not given. If it were given, probably we wouldn't need digital signature, because then MACs had almost the identical functionality, and we wouldn't need all this problem with long number arithmetic, blah, 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 blah. Okay? So what that means is offers no protection if Alice and Bob try to cheat each other. Meaning it's a dishonest person, the bad guy, if it's not Oscar, but it's either Alice or Bob, this thing doesn't work. Good. That was already chapter number 1 of today, and now the second chapter, which turns out to be a larger part today. We're going to talk about how to actually realize message authentication codes. So the title of the second chapter of today is Max from Hash Functions. So the question is, how do we realize that here? And what we want to do, we somehow want to bind together a key and a message, and a surprisingly simple approach is, basic idea, is to say, okay, our MAC M which has an input X, obviously the message, and the input K for the key, the secret. And what we now want to do is somehow use this hash function, which we just call H, which stands for the hash function, and somehow we use K and X as the input to the hash function. And then, they're really good with scrambling things together, and somehow this is the input, and we get an output, and then the output M here is a function of both X and K, and it's really hard to attack the system because hash functions have all these nice properties. That's the basic idea. So the question here is, how exactly do we mix K, X? Question mark. And essentially, there are two basic things we can do. The two ideas that seem obvious is, first idea is we say you first input the key K, and then X. And this symbol here, the two bars, means concatenation, Verkettung. So first the key, whatever, 128 bits, and then your 2 megabyte PDF file. This is the first thing you can do. And again, the hash function somehow scrambles everything together. What is the other thing we can do? You don't have to be super creative here, fantasievoll, to come up with what is the other thing we can do? Yeah. Flip them, exactly. Why don't we first do X and then we do K? So these are both, again, naheliegende, more or less straightforward approaches. As often in cryptography, they're both bad ideas. Okay, and so what I'm going to do now, and in part because HMAC, the actual HMAC, the final solution is pretty easy. The final solution is kind of a combining of those two. But I want to show you now is why there are weaknesses in both, to get you also a little bit of feeling how tricky cryptography can be. So both are weak, and both have names. So this is called the secret prefix. Does anyone know what prefix is in German here? Vorsilbe, right? Some pre is Vorsilbe. Secret prefix, because the secret is the first thing here, right? The key is first. And this is secret Nachsilbe, secret suffix, I think it's called. Yeah. So what we're going to do now, we're going to show weaknesses of both. I think it's kind of a fun thing to see, and then we, find a way to repair the whole situation. So this is 2.1. Let's give that this section a new name. Secret prefix max. You don't have to leave space. Very good question. Thank you very much. I like people that like a good script. Okay, very good question. So now what we have now to do, we have to go deeper into details. Normally we say, okay, let's hex here in both things, somehow X is being hashed. X could be a really long file, could be 2 megabyte PDF file or 2 gigabyte hard disk partitioning or whatever. So what's really happening, X is somehow divided in blocks and then we hash blockwise, which is going to be an important issue here. So X is really split into blocks. X1, X2, up to block N, where this is, the size, the length of each block is the input length. This is input width, Weite of hash function. E.g., SHA-1, anybody? What is the input width of one block for SHA-1? What is the block size that we feed into SHA-1? Anyone know? 512, okay. They're rather big, but they're still blocks. And now if we want to do secret prefix, meaning we first feed in K and then X. M is hash of K appended with X. We do K concatenated with X1, concatenated with X2, blah, 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 up to Xn. This is really what I'm trying to say here. If we write this here, first K followed by X, this is kind of on a more low level. This is what we're doing because X itself consists of multiple blocks in general. Now we have to look into details. How hash functions deal with that. Most hash functions use Merkel-Darmstadt, with our favorite Danish ladder construction. Okay, now we have to switch to the next board. Merkel-Darmstadt means we have the compression function here. We feed in X1 up to Xn. Here we do the iteration. And here we get h of x out. There's somewhat a simplification here. And here you do have an IV, an initial vector. That's roughly Merkel-Darmstadt. I'm skipping a little bit on a little detail here. So now now comes the attack. Let's look at Alice. Bob. So Bob does exactly what we wrote down here. He computes, they share a secret key, and all the key exchange works out nicely. So now he computes exactly what we showed up there. He computes k concatenated x1 concatenated blah, 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 up to xn. Bob is a nice kid, so he exactly follows the protocol. Protocol meaning compute the MAC, send MAC and message over across to Alice, across the channel. The problem is we're talking about attacks. We talk about attacks by third parties. We have mean little Oscar in the middle, and he doesn't like that. So he interferes at this point, and what he does, he computes this new message, which we call X index O, Oscar. I use this handwritten O, Schreibschrift O, so you can distinguish that from a zero, okay? That's not the point of infinity in elliptic curves. So now you have to, by the way, if people were asleep or talking, stop, okay? So this is kind of important. This is the one thing which is not completely straightforward. And it's not that easy to find in many books, what I'm showing here. So please pay attention. And it might be on the final exam. So many good reasons. Hallo, da, ja. Gute Gründe hier aufzupassen. 3 Minuten. So. This is the old message. What Oscar can do, and you have to judge for yourself whether this is a threat or not, he can append this message. This is x1, x2 up to xn. He can generate xn plus 1 of his own choosing. Okay? And if you think about, let's say this is a contract, a Vertrag, and at the end often you have appendices, Anhänge. And they're sometimes very important. What is really the appendix here? And he can come up, for instance, with his own appendix, his own Anhang. Okay? Now, and of course, now he has to compute an M for this whole message. And how can he do that? The problem has to do with this iterative nature here. Because, maybe I'll first write that down, which we call MO here, so that's the MO computed by Oscar. The only thing he has to do, think for a moment. This is this malicious new block. How would Bob compute that? Well, Bob would first feed in K here, right? Bob would have, if you want to have that here. So what Bob did is the following. He fed in x and then x1, x2, up to xn, up to here, and he does this iteratively. Okay? Now Oscar and if Bob would have wanted to include xn plus 1, the only thing he has to do at the end, he takes xn plus 1, feeds it here. And what is this value at this point here? If Bob wanted to do that, what value do we have here at this point? Yep. M? Exactly. M is the final output that he computed up to here. This is M. Very good. Well, but this is exactly what Oscar can do. Oscar gets M here. So he can hash. He simply hashes xn plus 1 and maybe with an index here, IV set to M because the switch would be in this position here. The initial vector that he's using would be M. So now he is forwarding to Alice his faked message, this faked contract with the faked appendix, with the gefälschte Anhang, together with the message authentication code. Alice is again a nice girl, so Alice just does what people told her to do, namely, please recompute the MAC. So Alice computes M prime, and what does she do? Well, she uses this approach, the prefix that means first the key, then x1, and the last thing she hashes is xn plus 1, which is exactly what Oscar did. And now she checks, is M prime really equal to M? And the output is this is a valid MAC. So this is a problem, okay? And this is a little bit simplification because in practice, this is not the whole Merkle-Darmstadt construction. So one important remark is attack does not work Do you remember what's missing here? There's this one block missing in this diagram that I used last week. Does anyone know? What I had in here was another block. And you know what this was called, what I did here? Padding, exactly. Pad. So what really Merkle-Darmstadt says is attack does not work if padding with, and not just any padding, but padding with length information. Is being used. Length information means in the beginning with the first block you somehow include the number of blocks or the number of bytes that are coming here. If you do that, of course, then it will fail because suddenly the message is longer than what you really expect. Okay? That means if you do strictly Merkle-Darmstadt with padding, this attack doesn't work. But if you have other hash functions, that don't do padding with length information, the attack work. Okay? So what I really want to show you here is this is an attack that can be a threat if you follow strictly Merkel-Darmstadt. It doesn't work. But nevertheless, this is not a good situation here. You know, so means in general, the resume of this discussion, the last 10 minutes or so, is don't do that because Oscar might be able to append bad things to the message here. Okay? So there's an attack available. So this was the upper one, secret prefix. So from this discussion, it seems as though we can do the other thing, which is chapter section 2.2, secret suffix, Nachsilbe. Secret suffix, what did they call that? Max. What is that again? This is, M is, we just had problems if we start with the key, you know, key and X, because then we could maybe append things at the end of X. So why don't we do it the other way around? We do X, and once X is being hashed, we include the key at the end. And now comes another problem, which is more closely related to properties of hash functions, which I think is a good discussion that follows now. Assume Oscar can find collisions What is that again? Collision means i.e., das heißt, he can find x and x0 such that this condition is fulfilled. And again, x could, for instance, be please transfer $10 into Oscar's account, and that could be please transfer $10,000 or euros into Oscar's account. Okay? So two contracts, two financial transactions, something like that, with different meanings, but the same hash output. Now, again, if you think about this iterative construction here, the Merkel-Darmstadt, basic Merkel-Darmstadt construction, so what happens now if you first you hash x, that means you do x1, x2 up to xn, you do that iteratively, and you get a certain output here at this point. And then you do this second thing with x0, again you have x1, x2 up to xn, but with a different message here. Okay? What happens then at the end of this iteration, you get the same output here, right? That's what we just discussed. But now, if we do secret suffix hashing, we append at the end the key here. And now we have a problem because in both cases you have the same value here. You have here h of x, which is equal h of XO, and now, in both cases, if you append X, you get the same output here at this point. Okay, if you do, I should really get rid of this here, right? You could wipe that out. if at the very end, if you input K at this point here, at the last block, in both cases, you have the same value here. That means in both cases, you get H of X concatenated K becomes the same as H concatenated X index Oscar concatenated K. Here. This is a problem here. From this is followed, just writing the last line down here again. Is equal to M. So both M values are the same, both max are the same. So in this case, the attack is even easier. And I don't even want to write that down. If Oscar intercepts, he doesn't even have to change M. He keeps M the same. He simply replaces X by XO, but he keeps M the same. So the question is this a problem? Again, the assumption here is Oscar has to do more work than with the previous attack. He has to find a collision, right, which is not something that we do on Sunday afternoon, right, with coffee and kuchen or something, right, collision finding. It's very difficult. So the question is still, does this give Oscar an advantage? So the question here is, is this a problem? I.e., does Oscar gain anything? Which really, so what is the discussion that follows now? And I think it's an interesting discussion. In order to run this attack, he has to do collision finding. What is the alternative? Well, the alternative is, which attack always works against Max with a Mac here? What can Oscar always do here? What is kind of the general purpose attack against symmetric cryptography? It's always, in principle, always applicable. Well, exactly. So he can always do brute force. So the question is, by collision finding, is this maybe easier than doing brute force, and then it would be a stupid idea, maybe. So what we have to do here, compare brute force effort with collision finding effort. And this depends on the situation. Surprise, surprise. And now let's look. One very concrete situation is example. The hash function is SHA-1. And K, if we use these bars, we mean the cardinality. Kardinalität, die Länge. The key space here is 128-bit. So these are very typical examples. SHA-1 is a super popular hash function in practice. 128-bit is a security level we very often want to achieve because, for instance, we use that together with AES, and AES has a cryptographic strength of 128-bit. So what we expect from here is we expect an attack complexity or security level, let's call that attack complexity, of 2 to the 128. Meaning an attacker, Oscar, has to run 2 to the 128 steps, which is lifetime of the universe or something. 2 to the 128 is a really big number of pretty much everything you do in life or computers do. Now, so that means and now Oscar has two choices. Either, he gets X and M, and he knows his construction, and he starts trying all keys. Key number 1, key number 2, key number 3, key number 4, key number 5. I'm not doing everything, so we run out of videotape if I would do that. I can't count up to 2 to the 128. This is the first choice. The other choice is, let's try to find collisions. And what is the magic word here? What kind of trick can he use here? How complex is finding collisions for SHA-1? Normally, again, you can do a brute force type of collision search, and you end up with, this is 160-bit output. So if you do this naive collision search on the output here, you have a complexity here of 2 to the 160. This was this weak collision resistance. But what is the better thing that he can do? Why is it not 2 to the 160? What is the trick he can play? What am I looking for? Which keyword? We did this little experiment here with this piece of paper a few weeks ago. Birthday paradox, exactly. Because of the birthday paradox, collision search for SHA-1 is not 160, but collision search takes approximately 2 to the 160 square root of steps. So this is roughly 2 to the 80 steps. Because, compare birthday paradox. By the way, did we find a collision here 2 weeks ago? Yes. I was really worried that the mathematics don't work, but they work. I wasn't really worried. I was just surprised. I mean, normally, actually, we do that, and very often, person number 19 who makes this little cross that, I have a collision. But it took longer here. So, from this, what is the conclusion from that? This is not necessarily a great idea if you use a hash function with the output length is not long enough, you don't really get this cryptographic strength. Suddenly you make your MAC attackable by the birthday paradox, and the attacker gains something. So, means the second secret suffix approach doesn't work. So the question is, what do we do? And there's luckily, and now comes kind of the cool thing, the thing that's being used in practice is kind of a little bit more complicated approach, but it's not really all that complicated. It's a little bit more complicated than this here, but it's not really complex. It's not another SHA-1 hash function or something like that. And this is called 2.3. This is the HMAC construction. Two remarks here at this point to start with. I like to give you a little historical perspective. Remember, DES was proposed in roughly 1975, and then 76, 77, both Diffie-Hellman and RSA, the big public key algorithm, were proposed. This was proposed in 1996 by Belair, Canetti, and Kroftschick, and I'm not writing the names down. And it's widely used in practice, e.g. in SSL, or which is also called TLS. SSL or TLS are this little lock in your web browser. If you get a secure connection to Facebook or whatever, and this little lock goes on, SSL and TLS are active. So what is the idea? The problem is, oh yeah, by the way, this is the problem with this collision. You cannot avoid, even if you do proper padding, blah, 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 you still have the problem here. The idea here, so that means we essentially want to stay away from secret suffix, but the secret prefix we can repair. So the idea at this point is use two nested, verschachtelt, right, ineinander eingenestet, I don't know what's a good German word, verschachtelt, two nested secret prefix max. So roughly, ungefähr, what we do roughly here is we compute. Maybe wait a second. Maybe yeah. Watch me. Don't talk for 40 seconds. I promise. Just everybody watch me. Don't. 40 seconds. So we essentially do secret prefix macking. So that means first K, and then X, and then we had the problem which we saw here. So and then what we do, we do this Verschachtelung, this nesting. We do a second one. Here. Okay. So again, you can go, watch YouTube or whatever you're doing on your laptop. So that's it. So, I'm kidding. Pay attention here. So what happens? We have two hashes, and this is called the inner hash. And this is called, surprise, surprise, the outer hash. And this is this nesting, the Verschachtelung. So this is the basic idea, and now I'll show you what the difference from this very simple algorithm line is that in reality you have to take care of the keys. You have to somehow do a padding with the key, a pre-processing of the keys. So now in reality, it's not quite as simple, but almost as simple. The proper HMAC construction does the following. X input and K. X, again, can be a 2 megabyte PDF file, but K might be a 128-bit key. Here's what you do. You do this outer hash, and instead of just using the key, you do the key and you XOR the key with the outer pad, which is called OPAD, not related to whatever. Okay. This is the first thing that you're doing. And you don't have to, and also you're not using the plain key, but you have to expand the key, so we call that key plus. And I'm going to, I promise, in 2 minutes I'm going to explain what this all means. And now with the inner hash, you do the same. You're not using the plain key, but you do some kind of pre-processing with the key. You have the inner hash, which does this, again, K plus. You have to somehow expand the key. And you do an XOR, but with a different mask, with an iPad. 1996, right? This was pre the real iPad, but this is what the literature uses. And I know it's confusing. And then you append X. So this is closed, and this is, maybe I use brackets here, maybe that's more. Is this correct here? I think so with the brackets. So what does that mean? It's not that complicated. So K plus is used in two situations. And this is not that complicated. What you really do is, if you use hash functions, very often you have this pretty long input block size, namely either in practice either 512 bits or 1024 bits. But the keys are rarely that long. You know, typical key is 128 bits, maybe 256. So what you do here, you append the key with zeros. So what K plus does is you do 0, 0 up to 0, and then you put the actual key in. So this is now hash block, hash input length. E.g. 512 bits. Everybody with me? This is 128 bits. If you want to go up to 512 bits, you need whatever, 480 something, right? And OPAD and iPad is even simpler. These are two fixed bit patterns. They're written in the standard. I didn't come up with them. iPad, this is 8-bit blocks 0011, 0110, which is 1 byte, obviously, and you just repeat the byte many, many, many times. And again, this is hash input length. If you're using SHA-1, you have 512 bits. This is 64 bytes. You do that, you have 64, you have a repetition of 64 times here. You do 64 times, you input this bit pattern. And the OPAD, so this was the inner pad, and now the out pad is a different bit pattern, but it's exactly the same thing. Is 0101, 1100, and again you repeat that, for instance, 64 times. We are done in 2 minutes, but you're not allowed to leave before you do the course evaluations. Okay? So, and now what I want to show you, maybe you're a little bit confused. I don't know whether you're confused. I want to show you a block diagram. So let's trying to get the beamer running. Just bear with me. Here we are. So what I want to show you here is compare this to figure 12.2. On page, and you might have a new edition of the textbook. I have the first edition, the first printing, on page 324. Maybe it's on 325. No, it's not. So this is the printing you have that you see here. So I just want to briefly discuss this. What you see here. We start with the inner iPad, and you combine that with the expanded key here, and you take this together with this whole long message, and you do one hash, which might take a long time. What is very important, just stop for 1 second. I know it's really exciting to do an evaluation. Just stop, please, 30 seconds, please, please. Does everybody stop? Bitte aufhören, 30 Sekunden. Ja, Sie auch, gut. Haben alle aufgehört? Just a very simple statement, very important. You look at that and you said, okay, that might be very secure, what Professor Parr says, but you have to do 2 hashes, which is kind of a lie, because even if you have a really long message, this is 2 megabytes. This really long message, you only have to hash once, the inner hash. The outer hash is only 2 input blocks, S0 and this here. That means the computational overhead, this extra work is very, very small. Because this main hashing of this long message you only do once, and then this outer hash is very short. You only have to do once. Okay? Go back to work. That's it. And you do that with initial vector, blah, blah, blah. And here, this is what I just said. And then the outer hash you do at this point here. I just want to write that down, the statement I just made. Maybe here. Note. Message is only processed in inner hash. That's it for today. Thank you very much.